All right, hi, differential equations. Let me first start by saying my co-ed class, the last Zoom class we did, I have to say I looked over what I wrote for that last Zoom class, and I think of all my Zoom lessons, that was the worst. I think I was not clear. I think I was very confusing. So there's that. For my all boys class, the last homework you had, there are probably half of the questions you couldn't do. And that may actually be true of my co-ed class too, because I just did a horrible, horrible job with that lesson. So this is going to serve as a redo of that last Zoom lesson for the co-ed class. And my boys class, you should now be able to finish the homework. So um, I apologize, boys and girls. I was very unclear. Okay. Here's what I'm going to do. I'm going to walk through case 3 here, and I thought it would be kind of a nice exercise just to um, read the text with you, and you'll see that the effort it takes to read a text, and I annotated where I needed to because they made some significant jumps here. But first, let's take a little detour for my all boys class, and let's just derive Euler's principle. So my all boys class happens to be an all BC class, which is interesting. So they will remember from last year the Taylor series for these 3 most popular Taylor series, okay? And then what I did in this step right here is all I did was I did a substitution. If e to the x equals this, then e to the ix equals this, okay? And then I simplified the powers of I, because powers of I can always be simplified. And when you simplify the powers of I, you'll notice, for example, right, the ix squared over 2 factorial, that becomes this term because I squared is -1. I cubed becomes negative I, right? Did I lose a power of 4 here? I think I did. Yeah, I did. There's a power of 4 right here, right? I to the 4th equals 1. So that's this term here, okay? But then what I want you to look at is when you do e to the ix, oops, that was a surprise. The highlighted terms is nothing other than cosine x. And the non-highlighted terms is none other than I times sine of x. And therein lies Euler's principle, right here in this red box. Euler's principle is pretty fascinating if you think about it. I mean, just think about the relationship here. What they're saying to you, and this just kind of defies all reason, is that e raised to some imaginary power is equal to cosine x plus I times sine x, okay? And probably the most popular specific case of Euler's principle is if you let x equals pi. And if x equals pi, Euler's principle becomes this specific case, e to the I pi equals -1 plus 0. And when you write it in this form, e to the I pi plus 1 equals 0, it's very delightful. It's delightful because what you have in this equation right here are the 5 most famous, most significant, most powerful symbols, all related in one equation. Albert showed Cameron and I this version of it, which, there's nothing wrong with this whatsoever, right? When you write it like this, it's the exact same thing, but it's not quite as delightful because, it's just cleaner. If you can have plus instead of minus, it's generally a cleaner and more aesthetically pleasing for mathematicians. And then there's no 0 in this version, right? So this is probably the most famous specific case of Euler's principle. It's really just phenomenal. I think it's so fantastic. And this is arguably the most beautiful equation in the world. It comes straight from, inarguably, it comes from our understanding of Taylor series. And it comes from a really, really powerful contradiction, which really is that, someone always has this argument, like sine x, cos x, e to the x, they equal these polynomials, but only if these polynomials go to the infinitieth power, if you will, right? So some would argue Euler's principle is like this big hypothetical. I guess I agree with that to some certain degree. It's also kind of like this, I think of it almost as religion, right? Like you take Euler's principle as fact if you can sit comfortably with the notion that really this equation exists if and only if you embrace the likelihood and the possibility of the infinite, which is quite beautiful statement. Okay, so now we can go to case 3, okay? So case 3, as you know from our last notes, not the last lesson, co-ed class, okay? That last lesson, I'm sure I confused you. So this is case 3. When you, case 1, let's remember. Let me see if I can pull up that. Case 1, if you remember, is, where's case 1? Case 1 was, where was it? Is this it, case 1? Okay, yeah. Case 1 is if you have, we're talking about second order differential equations, homogeneous, HDs, constant coefficients. So case 1 is when you have y equals e to the mx as the characteristic solution. That's when your auxiliary equation has 2 unique real roots, okay? Then you have case 2 when you, wait a minute. This is not, oh, I'm pointing at the wrong thing. Good grief. I should be pointing right here. I'm looking at my word like, what? Right, here's case A, I should say. Okay, so we talked about case A and case B. Case A, if you have 2 distinct real solutions. Case B, if you have a repeated or a multiplicity. Okay, then here's case 3. So case 3 is the discussion today. So if you have case 3, where when you solve for m, you have complex roots, and they call those roots alpha plus I beta, right? We called it probably in our trig textbooks and TIC, we would call the roots m equals a plus or minus bi, right? They just use alpha and beta for no real reason, okay? And if m equals a plus bi, right here, we know that the general solution, right? This is the general solution is this, by the principle of superposition, okay? Now, what I'm going to do right here is I want you to look at my purple. I'm going to annotate your notes here for a minute. This, by properties of exponents, is no different than, right, e to the alpha x times e to the ibx. That is equal to this expression. I just distributed the x, and I know e raised to the sum of powers is the same thing as e raised to different powers and multiplied. And the same thing could be said right here. Okay, and then all I did here was I just factored out e to the alpha x. Okay, so here's e to the alpha x, and then here's what I'm left with within. Okay, ignore the pink and the blue for a second. Okay, now what's going to happen is, don't forget, don't lose sight. This is the general solution. Okay, so this talks you through this. It takes you to the conclusion by way of, let's just make sure we understand. These are the roots of the auxiliary equation by the principle of superposition. This right here is a general solution. Okay, let's not lose sight of that. Now what we're going to do is we're going to use Euler's formula or Euler's principle. I always call it Euler's principle. It just sounds more sophisticated than Euler's formula. We're going to use Euler's principle to just flesh out this pink e to the ibx and the blue e to the negative ibx, okay? Well, according to Euler's principle, e to the ibx equals this. And e to the negative ibx equals this. Because, remember, this comes from right here, right? E to the ix equals cos x plus sine x. If you substitute bx in for x, right, you'll get cos bx plus I sine bx. If you substitute in negative bx, you'll get cos negative bx, I sine negative bx. Okay? All right. So now, again, don't lose sight. We're just kind of fleshing out, teasing out this pink and blue here. Okay? And then what we're going to do here is, this is just kind of a nifty genius trick. We're going to take these 2 expressions here and add them. When you add them, you'll notice that the I sine beta x and the negative I sine beta x cancel, and you get this. Okay? When you subtract these, we will get this. Okay? Notice here, you have to account for the trigonometric identity. And Nancy, this is where Nancy caught I dropped the negative here. And thank you, Nancy, for that. Okay. trig identities. Don't forget, the cosine of theta is equal to the cos of negative theta. By similar measure, I'll write this down, the cosine of theta equals the cosine of negative theta because of the way the quadrants work for cosine. Cosine goes positive, negative, negative, positive, right? So the cosine of positive theta equals the cos of negative theta. By similar measure, the sine of theta equals opposite sine of negative theta, right? Because the way sine works in the quadrants, it goes positive, positive, negative, negative. Okay. Another way of seeing this is sometimes it's written like this, but this is the same statement as saying negative sine theta equals sine of negative theta. And Nancy, here's where you caught me when I lost a negative. Okay. So when you use these trig identities in conjunction with adding pink and blue and subtracting pink and blue, we end up with this. Okay. We end up with that. Now, what that does for us here, I'm going to pause us for a second here because I'm going to annotate and add something pretty significant. So give me 1 second to add that. Okay, so this is the very important piece here, and I hope you're appreciating how it's really difficult to read a math textbook, and the higher level, the higher you go, the more difficult it is. Okay, so you're hopefully wondering, why on earth would I kind of go through the hassle of adding pink plus blue and subtracting pink plus blue? Okay, well, let's go back up here. Remember, what this is a general solution. This was a general solution, general solution, general solution. And a general solution means it is true for any possible values of constants C1 and C2. It's a general solution. So if I were to ask you, well, let's just pick a value for constant 1 and pick a value for constant 2. Well, I'm going to choose to pick C1 equals 1 and C2 equals 1. The important point to make here is if you pick a constant for C1 and a constant for C2, what you are doing is you're saying, okay, here's my general solution, and I'm going to pick C1 and C2 to yield a particular solution. So appreciate this process here. It's really incredibly savvy. We're going from a general solution and we're picking a particular solution, C1 and C2 to equal 1. And the reason why I want to pick that particular solution is, you'll notice, if I put C1 and C2 equal to 1, look what happens to this expression. It becomes e to the alpha x times the quantity, e to the ibx plus e to the negative ibx, because C1 and C2 equal 1. Well, what do we know about this? E to the ibx plus e to the negative bx is none other than 2 cosine beta x. And here we are. So what we've just done, everyone, is we have now, and look at my subscript, I'm calling it y1. I'm not calling it y, because this is now a particular solution. Okay? Now, I'm going to choose another choice of constants 1 and constant 2. And this is where they talk you through right here. Just read this part right here. Okay? If you pick C1 equals positive 1 and C2 equals negative 1, right? Look over here. If you pick C1 equals positive 1 and C2 equals negative 1, you will get another particular solution. And that second particular solution, let's make sure we emphasize the particular, is none other than y2 equals e to the negative alpha x. And what's going to be inside? Yes, inside is going to be e to the ibx, or 1 times e to the ibx, minus 1 times e to the negative ibx. And that is none other than 2I sine bx. So, okay, and once again, be very, very mindful of the fact that these are particular solutions. You have gone from a general solution, we've never done this before. We took a general solution and we picked savvy values of the constants to give us two particular solutions, okay? That's what they're talking through right here. I really don't like the fact that they don't emphasize, general versus particular. But what's happening right here in these steps is you're generating two particular solutions. And they are particular because you picked particular values for those constants. Now, once you have two particular solutions, everyone, and this is we're just assuming for right now, it's a second order HDE. Well, what could you do? Well, now look what we can do. We can say that in general, the general solution to this HDE is constant 1 times y1 plus constant 2 times y2. And that gives us my general solution right here, okay? So what we just did was we went from general solution to a particular solution back to a general solution. What's the advantage of this? Okay, there are several. There's one big one though. What the all boys class is seeing for the first time is that while this general solution at the top is valid and correct, you will notice the general solution presents as a linear combination of exponential functions. However, what Euler's principle allows us to do is to include and rewrite a linear combination of exponential functions as none other than a linear combination of particular solutions that are now inclusive of the cosine and the sine function. Okay? So what I want to do here is I want to tie this up together for you. Okay? What we're saying here is that the general solution now, and there are two versions, right? Is, let's see, C1, so C1 times Y1, e to the alpha x times 2 cosine of bx, we'll clean up in a minute, okay, plus C2 times e to the negative ax times 2I sine bx. Okay, now I'm going to make this look a little nicer because if you look at this expression, constant C1 times 2, that can just be, a constant in of itself. So this becomes e to the alpha x. I'm also going to factor in e to the, well, actually, no, I'm not. Let's do this. Hold on a minute. Uh-oh, why did I lose a negative? Hold on a second. Why is there an extra negative here? Oh, yes, there's a negative here for some reason. How'd that get there? There shouldn't be a negative there. Good grief. There shouldn't be a negative here, nor there should be not a negative here. I don't even know why there was a negative there in the first place. Dagnobbit. Okay, anyway. All right. I'm going to factor in e to the ax out. E to the ax out. Oh. Factor in e to the ax out. And then I'm left with, okay, look what inside. C1 times 2 is none other than a constant. C1 cosine of bx plus, now look what I'm going to do here, C2 times 2I. This is the first time you're going to see us kind of include I as a constant. I mean, there's no rule saying that the constant can't be imaginary. So all I did was I took C2 times 2 times I and I plopped them into right here, C2. Okay? And what we have here is my general solution to an HDE if there are complex roots. And you will notice, I made a note here, I said, note the nature of C1 and C2, right? The nature of C1 and C2. C1 is real. C2 is imaginary. Now, I will also say to you this as well, this is the general solution if your solutions to the quadratic auxiliary are m equals a plus bi. But you'll notice if b equals 0, what happens if b equals 0? If b equals 0, we just have case A of a quadratic auxiliary that yields 2 real roots, right? If a is 0, we have, if a is 0, then this factor out here becomes just e to the 0, which is just 1. So this is actually, case 3 is the most inclusive of all the cases, okay? Now, what I want to do is, so this was really fantastic. I mean, the process is really fantastic. And I know for a fact, co-ed class, when I blitzed through this with you all, I'm absolutely positive I confused you, because when I looked at my notes, you want to see what they look like? Yeah, like I went through this and not only that, but then, I dropped a negative. Like, what on earth happened? No, this wasn't it. These are my things. Was this it? Yes, it was, right? And I did this and this and this. Yes. So basically we did it, but I am 100% sure that I lost you in the way and it wasn't nearly as thorough. Okay. I hope that was nice and thorough. Here's what we're going to do. We're going to go now to homework. This was the homework you had. And I'm going to take a look at, okay, the ones that my boys class definitely would not have been able to do are 25, 39, and then B, D, and E. Let's just do 25 together, okay? 25. So 25, this is one that we can now do fully. 25, when when I use the characteristic solution of y equals e to the mx and I do a substitution, I think you will all find that we land here, okay? M equals plus or minus I root 3 over 2. Notice here, this is just M equals 0 plus or minus I root 3 over 2. So A equals 0, okay? Now I want you to notice something. If you look at the factors from which the values of M came, each of these solutions, positive I root 3 over 2 and negative I root 3 over 2, they're each going to be of multiplicity 2. Luckily, we know what to do when there's a multiplicity 2, okay? Now, we know, this is where, now be careful and look at my subscripts here. What I did here for 25 is I went and found how many unique solutions? 4. There's got to be 4, because for an HDE constant coefficients, the order of the Diffie gives you the number of unique solutions. So what I did here was I know that the first two, y1 and y2, are 2 cos radical 3 over 2x and negative 2 sine radical 3 over 2x. How do I know that? Look over here, okay? When you have got this, you know, right? You always know that you're going to have 2 particular solutions. And these particular solutions, again, we pick it, we just choose a savvy value of C1 and C2. So a particular solution will always be e to the ax times 2 cos beta x, e to the ax times 2I sine beta x, okay? Now, alpha here equals 0. So when you've got this, e to the ax, e to the 0, that actually equals 1. So this is, unwritten, understood, it's e to the ax times 2 cos beta x and e to the ax times 2I sine bx. Whoops, I lost my I. Hang on a second. Okay, see, I fixed it right there. I also don't know why I had the negative there. I don't know why the negatives keep getting to me. It's very odd, very odd. And once again, there should be an I here. Anyway, I'll get there in a second. Okay, so these are my 2 particular solutions, right, that I know have to exist. But each of these solutions is a result of a value of M for which there's a multiplicity of 2. What does that mean? Well, we know that if y1 is a solution, and this unique solution comes from an M value of multiplicity 2, well, we know that y3 is going to be x times this unique solution. So do you see how I did x times 2? I just wrote it as 2x, right? Similarly, y4 is going to be x times y2. And once again, I have this negative and I dropped the I. It's very odd. I don't know what I'm doing, why I'm doing that. I don't know what's going on in my head when I do that. Very interesting. So now I found my 4 particular solutions, and now I can say my general solution. And look what I have. The general solution by the principle of superposition is y equals C1 times Y1. Notice C1 and the 2, I amalgamated those. C1 times 2 is just a constant. Plus, look at C2. C2 times 2i is just a constant. Plus C3, a constant C3 times 2 is just a constant. And then C4, a constant times 2i is just a constant. And here at the end of the day, you have your general solution. Okay? Probably the most meaty of all lessons that I've done thus far. Okay? And once again, I don't know why I keep dropping. I'm looking at 39. I did it again. That's so interesting why I keep doing that. I've got to go back in my head and see what I'm thinking of. Why is that negative keep coming in there? In any event, I hope that helps. What I'm going to have you do is just for both sections, I'm going to post it on both classes. And I guess my co-ed class you dropped today. You're going to notice that this is on the docket for Tuesday, okay? And I'm going to have you re-look at this assignment and now do 25, 39, and then, of course, B, D, and E. I think I did B here with you, right? So B, no, did I do B with you? Maybe not. Maybe not. Okay, but that's where we'll leave off, all right? I hope that helped co-ed class. I hope that made sense of the mess. And boys class, I hope that shed some light on your last homework. And if not, we will talk next time, okay? All right, goodbye.